All right. So as I mentioned, tonight we are going to start in on our chapter 3 work. What I will say is, just as with the first exam, if you aren't happy with how you performed on this exam, remember I do allow you to replace your lowest regular exam with the grade that you get on your comprehensive final exam. But you only get to do that for one, right? So if you didn't do great on exam 1 and you didn't do as great on exam 2 as you had hoped, you only get to replace one of them, not both of them, okay? So keep that in mind. And then for the final exam, 75% of the final exam will actually be made up of exam 1, 2, and 3. So I'll tell you which topics to really put your focus on from those for that comprehensive final. Okay, so let's shift into our discussion on inverse functions. So if you recall, we've talked about what it means to be a function in chapter 1. So now we're going to say, okay, now that I know what a function is, right? Our functions, those things pass that vertical line test, right? So now we're going to look at what does it mean to be a one-to-one function. So if you recall, when we had our function, every x mapped to a unique y, right? But multiple x's could go to multiple y's. Now, when we're looking at something that is one-to-one, every x goes to exactly one y, and every one y is mapped from exactly one x. So we're not going to have instances where two x's produce the same y. Okay. And so when we get that, that's what we call one-to-one. Okay. And so that's really what that up at the top of the page is telling us. So basically, when we look at everything, every x has to map to exactly one y. So when we look at this, we have no repeat x's, but we do have this repeat y right here, right? So we have the same y with a different x. Okay, therefore this is not one-to-one. Okay, so even though it passes the test of a function, because every x maps to a unique y, it is not one-to-one because every x only maps to one y in its grouping. But because we have two x's mapping to the same y, we are not one-to-one or that exclusiveness. Okay? Question. So we can see over here in the picture on the right that it's a little clearer, right? Every hero maps to a unique villain, right? But had, Batman mapped to Sabretooth and Wolverine mapped to Sabretooth, then that would not be one-to-one. But because everything in the green circle maps to exactly one thing in the blue circle, then yes, this here is one-to-one. Okay, question. Okay, so let's look then here. If we're still trying to look and determine if this is one-to-one, now we can do what's called a horizontal line test, right? So before, to be a function, it has to pass the vertical line test. To be one-to-one, it has to also pass the horizontal line test. And so we can look and see if I draw a line for every one of these points, you can see that no line has more than one intersection. So yes, this is going to be 1-to-1. Okay. Whereas if this next graph, we draw one line here, and we can see it intersects our graph from the line we drew, it intersected our graph in 7 locations. So no, even though this is a function, right? Because if I did the vertical line test, it passes. It's a function, but it doesn't pass the horizontal line test. Therefore, it is not 1-to-1. Okay. And then we can do the same for this one. And you could see that we only ever intersect the graph in one location when we draw that. So this graph would be a 1-to-1 function. Okay. Question. Okay. So if we use the definition of 1-to-1 to help us determine here, so we want to show that if we evaluate our function at A and it equals our function at B, then A has to equal B. Okay. So let's just evaluate our function at A. So we're just going to say f of A, set that equal to f of B. So evaluate our function here. So that's 3A plus 2 is equal to 3B plus 2. Okay. We'll simplify this. We can minus 2 from both sides. We end up with 3A equals 3B. Divide both sides by 3. And we get that A is equal to B. So because these two conditions are met, yes, that is going to be 1-to-1. Okay. Question. Let's look at this example. So again, set f of A equal to f of B. So that gives me 3A squared is equal to 3B squared. We could divide both sides by 3, and then we get A squared is equal to B squared. Take the square root of both sides, and we get A is equal to plus or minus B, right? And therefore, we have A isn't equal to B, so no, this one, because A is not equal to B, so no, that is not going to be a 1-to-1 function. Okay? Because A maps to positive B and A maps to negative B. Okay? So just that reminder, when you take the square root of something, it's both the positive and the negative, right? Because negative 2 times negative 2 equals positive 4, and positive 2 times positive 2 is also positive 4. Okay. All right. Question. Okay. So now let's look at the composition of function. Okay. So if I'm looking at, so when you see this, where we have this little, it almost looks like a degree symbol here, but it's not. So that really is the symbol for composition. So you would read this as f of g, right? This reads as f of g of x. That's how you would read that line, okay? And so basically we can, when we're looking at that, if we want to determine if something is an inverse, right? So we can so f of g of x, I'll get an answer, and g of f of x, I'll get an answer. And if those two both reduce down to x, just x, then they are inverses. If they don't reduce or simplify down to x, then they are not inverses of one another. Okay. So looking at it in an example is probably a little clearer to understand than reading it off of the formulas up there. So let's look at that. So we have f of g of x, okay? And so really that's just saying I take my f function and everywhere I have an x, I plug in my g function, okay? So in this case, I'm taking my f function, that's 3x, plugging in my g function, plus 6, okay? So this gives me x minus 6 plus 6, so that simplifies to x. That meets the first piece, okay? But we have to test the other way as well. We have to test g of f of x, okay? So that is, we're taking our g function, substituting in our x, or f of x function, okay? So my g function is 1/3 x, plugging in my whole f function, minus 2, okay? So this simplifies as x plus 2 minus 2, and it simplifies to x. Both of those simplified to x. So yes, this is a one-to-one function. Okay? Question. Okay, let's look at another example. So again, let's do f of g of x. That is my f function. We're going to substitute in our g function. So we have x, so that's 5x plus 1 for my g function, plus 1 over 5 into the rest of my x function, or my f function. So this simplifies to 5x plus 2 over 5. This is not equal to x, so it doesn't look like these two functions are inverse. But let's just, for practice, do our g of f of x. That is taking our g function and plugging in our f function. So I get 5 times x plus 1 over 5 plus 1. So this gives me, the 5's here cancel. So this gives me x plus 2, which is not x. And so we can see again. And so therefore, these are not inverses. Okay? Question. Okay, so what if I only have one equation and I want you to tell me what is this equation's inverse, right? So I've only gotten one, so I need you to tell me what the inverse is. So in those sort of cases, you're going to follow through these 4 steps. First, you replace f of x with y. Then you change the x and y variables. So everywhere you have an x, make it a y. Everywhere you have a y, make it an x. Then you're going to resolve the problem for y. And then you'll replace the y with the f inverse symbol. Okay? So let's walk through a couple of examples of this. Okay? So the first one here we have, if I give you the function f of x equals 2 plus 1/2. Remember, step 1, we're going to just replace f of x with y. Okay, so all we've done is replace this with y. Okay, let me do that. in color. Okay. Step 2 is we're going to take this exact same thing here. We're going to copy it. But now what we're going to do is we're going to trade places with our X and our Y. So this becomes X and this becomes Y. So all we're doing in this step is trading spaces. Everywhere we see an X, we make it a Y. Everywhere we see a Y, we make it an X. Okay. Now, step 3 is we're going to solve for Y. Okay. So we can minus 2 from both sides. So we get, I'm going to put the 1/2 Y on the left because I like my Y on the left, equals X minus 2. Okay. We can now multiply everything by a 2, right? So that gives me Y equals 2X minus 4. And the 4th step, right, was to take our final solution here. We're going to just copy it down, but we want to replace the Y with the F inverse of X. Okay, question. So the inverse of that function that we were given in the beginning is just 2X minus 4. Okay. And we could graph this if we wanted to. So we'd come over here to -4. That's where we have our intercept. And our slope is 2. So we rise 2, run 1. Let me do this a little better. Rise 2, rise 2, rise 2. So that is what that graph there, that would look like if we graphed it out. You could also test to say, to just check our work. We won't do this on all of them, but if I did F of F inverse, right, that's going to give me 2 plus 1/2 times 2X minus 4. That simplifies to 2 plus X minus 2, which equals X. That is what we need, right? We have to do the same for F inverse of F. That would be 2 times 2 plus 1/2 X minus 4. Simplify this, we get 4 plus X minus 4, which equals X. And you can see that both of those simplify down to X. Therefore, they are, in fact, inverses of each other. Okay, questions? Okay, here is another example. So this one, again, step 1, let's just say Y equals 3X over X plus 1. Step 2, let's trade our X's and Y's places. So we have X equals 3Y over Y plus 1. Notice that all X's get changed to Y's and all Y's get changed to X. Excuse me. Okay. Then our next step, we need to solve for we're going to resolve for our Y. Okay. So to do that, we need to do a couple of things. So the first thing, we can multiply both sides by y plus 1, right? Because whatever you do to one side, you have to do to the other. So we end up with, these will cancel out with one another. And we are left with xy plus x equals 3y. Okay. We can minus xy from both sides to get our y's over on the same side. So this gives me x equals 3y minus xy. So now we can factor a y out of the right-hand side. So we have x equals y. That'll leave me with the 3 minus x. Now I could divide both sides by the 3 minus x. And that leaves us with y equals x over 3 minus x. And that's our third stage. And our fourth step was simply just f inverse is equal to x over 3 minus x. Okay. And if you wanted to test this, you could do f of f inverse, see if it does pan out down to an x, simplifying, which it will. And then you can also do f inverse of x, and you will see a similar situation where it'll simplify down to x to signify that it is indeed an inverse function. Okay. And then I'll just show you over here an inverse function. So for this one, you will see it'll map a little like this. And you'd be down, this one is 1, 2, 3 over here. So 1, 2, you're coming off of here like this, right? And so that's really what an inverse function looks like. Question. All right, so here we have another inverse function, but this one, normally, because remember when we have that x squared, we're not going to be able to have an inverse, right? Because I have, if I did x equals 2, that would equal 4, but -2 also equals 4, right? So we're restricting our domain for x's, only the positive x's, and therefore this will have it will have an inverse because we're restricting the domain. If we didn't restrict the domain, though, then it would not work because it would not be 1 to 1. Okay. So we have y equals x squared plus 3. Again, keeping in mind that x has to be greater than or equal to 0. Let's change our x and y values. So this gives me x equals y squared plus 3. So y has to be greater than or equal to 0. When we simplify this, we can minus 3 from both sides. So this is going into step 3, solving it. This gives me y squared equals x minus 3. Okay. And when we take the square root of both sides, we get that y is equal to plus or minus the square root of x minus 3. So our inverse of our function is just the positive one, because remember, we're saying y has to be greater than 0. So we're looking at y is greater than or equal to 0. Therefore, we're only taking the positive piece of this. And I'll circle that positive piece in red because of the domain restriction. And you could put that in, this is step 4, where we're replacing y with that f of inverse, okay? If you put this through our f inverse and f inverse of f, you will see that those both reduce down to x, and therefore they have an inverse. So this one, you can see this point right here is 0, 1, 2, 3, 4. So we're switching. So we have 1, 2, 3, 4, 0 is one point. You can see another point. Let's look at this one. That is the point 2, 7. So let's look at 7, 2. And so that would be the inverse of that function, right? So notice, whenever you're looking at the inverse, all you're doing is all of the x, y coordinates on the previous graph become y, x coordinates that you plot on the one you're looking at for the inverse. Okay, question. The square root of 0 is 0. Because 0 is not positive or negative, it's just 0. Okay. All right, so here's an example to where it's the last thing out of this section. And you could see the graph of the function, and we want to graph the inverse. Okay, so the first thing, let's just see the points. So we have 1, 4 as this point, right? This is 1, 4. We have -1, 2. That's this, -1, 2. 1, 2, 3. This is -3, 1. And this is -4, -2. Okay. So when we're looking at the inverse, really, we just need to switch our x and y. So this becomes 4, 1, 2, -1, 1, -3, -2, -4. So let's plot those points. I'm going to do those in, let's do it in a different color. Okay. So actually I'm going to not choose this orange since that line. Let's just use purple. Okay, so we have this point 4, 4, 1. 1, 2, 3, 4, 1. We have the point 2, -1. We have the point 1, -3. And we have the point -2, -4. So that is what that inverse graph of the blue line would be the purple line. Okay, question. All right. So that was section 3.1. So that's just getting us a little bit of a taste of what inverse functions look like. In section 2 here, we're going to look at exponential functions. So an exponential function, if you recall, we're used to looking at x squared or y equals x cubed minus 1. Now we're going to flip and our variable x is going to be up in the exponent instead of down as the base. Okay. So how do we graph things like that? Short of, well, we're going to start by looking at graphing it, build a table. What does that look like? But eventually we don't want to have to build a table every time we want to graph something. Okay. So first, let's just look at if we had -3, -2, -1, 0, 1, 2, and 3. Okay. So if I'm looking at this function 3x, 3 raised to the x, so this would be 3 raised to the -3. So just a refresher, you guys probably already all know this, but just in case you've forgotten, I'm going to give you a little quick reminder. If I have an exponent that is up in the top, let's just say if I had x to the -2, that is the same as saying 1 over x to the +2. Okay. So when I have a negative exponent, I can bring it down to the denominator and the sign of the exponent changes. Okay. Similarly, if I had something like 1 over x cubed, let's do -x cubed, that is the same as saying x cubed, because when I have this negative, I can bring it up and make it positive. Okay, so just a quick refresher. So this is the same as saying 1 over 3 cubed. 1 over 3, so that's 3 times 3 is 9 times 3 is 27. So that is 1 over 27. Okay, this would be 3 to the -2. So that's 1 over 3 squared. So that's 1 over 9. This is 3 to the -1. So that's 1 over 3 to the +1. So that is 1/3. This is 3 to the 0. Anything to the 0 is 1. This is 3 to the 1, which is 3. 3 squared, which is 9. And 3 cubed, which is 27. Okay, so now let's just plot this graph over here. So -3 is 1/27. So it's really, really small. Notice that this scale here, my y is going in increments of 3. So -2 is 1/9. -1 is 1/3. 0 is 1. 1 is 3. 2 is 9. And 3 is 7. So you can see that this graph gets really big really quick. Okay. Question. So this would show you a graph of exponential growth, right? So this is growth because it's positive, it's increasing. Okay, so it shows growth. This next example, you see the exponent here is negative now, right? So again, that is the same as saying 2 to the -x is equal to 1/2 to the +x. Or the same as saying 1/2 with the x down here. Okay? So they all mean the same thing. So let's look at the -3, -2, -1, 0, 1, 2, and 3 example again. So now this one is going to be 2 to the -3, which is 2 to the 3, which is 2 times 2 times 2, which is 8. 2 to the -2 is the same as 2 to the 4. I mean, not 2 to the 4, 2 to the 2, which is 4. Okay? 2 to the -1, 2 to the -1 equals 2 to the 1, or 2. 2 to the -0, well, 0 is neither positive nor negative, so that is 2 to the 0, which is 1. This is going to be 2 to the -1, which is 1 over 2 to the 1, which is 1/2. This is 2 to the -2, which is 1 over 2 squared, which is 1/4. And this is 2 to the -3, which is 1 over 2 cubed, which is 1/8. Okay? So we can graph that. We have -3, 8, -2, 4, -1, 2, 0, 1. 1 is 1/2, 2 is 1/4, and 3 is 1/8. Okay, so you could see this one here. We have what you would call a decay, because our graph is, we were really, really, really high positive infinity with our y, but as our x moves to positive infinity, we quickly drop down and get really, really, really close to the x-axis, where our y is equal to 0. Okay, question. All right, so just as we had transformations and shifts with our chapter 1 stuff, when we talked about transformation, these logarithmic and exponential functions that we're going to cover tonight can also be shifted. Okay, and we can use our transformations to help us with this. Okay, so what we have here is the K out here tells us if we're shifting up or down, and any value associated with the X up in the exponent, that's going to help tell us if we have a shift to the left or the right. And then this A in front is going to help us with any reflection. Okay. So first, let's look at our function here. We're going to look at it in terms of just graphing it, or like building out the table. And then how can we look at it in terms of those transformations and see if we could have graphed it also just based on transformation. Okay. So again, I like the -3, -2, -1, 0, 1, 2, 3. It gives us enough options. So this one would be 1 minus 2 times -3 plus 1. And this is going to be 1 minus 2. It is what it ends up being. Not 1 minus 2. Sorry. 1 minus 2 to the -2. So this is going to give us 3/4. Let me see. For the second one, we end up with 1 minus 2 to the negative 2 minus 1. So that is 1 minus 2 to the negative 1. So that is going to give us 1/2. This is 1 minus 2 to the negative 1 plus 1. So that's 1 minus 2 to the 0, which is 0 because we have 1 minus 1. So that's 0. This one ends up with the 0. We end up with 1 minus 2 to the 1. So that is going to give us a negative 1. This is 1 minus 2 squared. So that gives me a negative 3. This would be 1 minus 2 to the cube, which will give me 1 minus 8. So that's a negative 7. And then 1 minus 2 to the 4th, which is 16. So 1 minus 16 is a negative 15. Okay. So if we were to graph this one, we would have negative 3 and 3/4. We would have negative 2 and 1/2, negative 1, 0, 0, negative 1, 1, negative 3, 2, negative 7, and 3, 15 would be somewhere down here. Okay. So that is what our transformed or our shifted function would look like. And if we were looking at just the parent function, right, looking at the parent of just 2 raised to the x, I think that we did that one. Well, we did 3 raised to the x, but it'll look like this, but instead of a magnitude of 3, it's going to be a magnitude of 2. So it would look something a little more along the lines. Here's 1, 2. It would look more along those lines, right? So those are the inverses of one another. And so if we wanted to look at this in terms of how we could use our pieces of the reflections and transformations, how could we do that, right? So when we look at this piece here, that tells us that we are 1 unit to the left. Okay. If we wrote this, let's write this in the standard form. So this is actually negative 2x plus 1 plus 1. So this right here tells us 1 unit to the left. This is telling us 1 unit up. And this right here reflects across the x-axis. Okay. And so when we look at that transformation, our blue one is our parent. We've shifted it down 1 unit. We've shifted to the left 1 unit, and we've reflected across the x-axis. Okay. Questions? Okay, so now let's talk about E, this universal constant. If you guys are familiar, we just recently had Pi Day on the 14th of March. And pi is one of those irrational, never repeating, never ending numbers. And so E is similar to that. It is also an irrational number. And as our x gets infinitely larger, then our expression gets closer and closer to this number we call E. And if you look on your calculator, you could push the E character and it will return this 2.718 and so on, decimal value. Okay. So if you have a calculator, go ahead and get that out so you can practice. If you don't have a calculator on you right now, if you have your cell phone, you can't use a cell phone on your exam. But if you have your cell phone on you right now, you can go ahead and break it out. Turn your cell phone sideways and you should be able to see the E character. Okay. So if you put in your calculator E squared, so it may look like E, the caret, and then the number 2, right? Hit enter. You should get a value of 7.3891 if you took that out to 4 digits. Okay. So why don't you guys take a minute, put E raised to the -3, and put what you get to 4 digits in the chat for me. So Brandon, that is a high number. So when you put E caret, maybe try putting parentheses around the -3. Or make sure everything is cleared out of your memory and it's not storing something else in there. Yeah, so you're going to get approximately 0.0498. Were you able to get that, Brandon? We want to make sure you're able to do that. Okay, perfect. Sometimes it's like if something's like still cached in the system, it might give you an error. All right, so what about if we do E raised to the square root of 7? What do you guys get? If you don't have the square root, I'll tell you another little trick. Like, let's just say we have the square root of 2. That is the same as saying 2 raised to the 1/2. So when we get the E raised to the square root, yep, that is 14.0940. And then lastly, when we do E raised to pi, we get 23.1407. Okay. So you guys will probably find yourselves using this E character on your calculator for this week's assignment. The one thing I will tell you, if you happen to not have a calculator and you can't access the E button, you can use this, but you need to use at least 4 decimals so that you don't get rounding error. Okay, so if you don't use at least, if you just did 2.7, you're going to get rounding errors, and so you might get the problems wrong, especially in the homework. Okay, any questions on the E character and how to use it on your calculator? Okay, so we may see E in our, as our base. So E raised to the X plus 1, etc. So again, let's do -3, -2, -1, 0, 1, 2, and 3. Okay. So this is going to be E to the -2. That's approximately 0.1. This is going to be E, so -2 plus 1, so that's -1. So this is about 0.4. I mean, we could write this out to 4 decimals here, but we don't have the fidelity to graph this graph over here, even to the 0.1, let alone 0.09872 or whatever it comes out to, right? So one decimal is sufficient for this graphing purposes. This is E to the 0, so anything to the 0 is 1. The next one is E to the 1. E to the 1 is 2.7. This is E squared, so that's 7.4. E cubed is 20.1. And E to the 4 is 54.6. Okay. So when we look at this, we have -3.1. It's so small, we're practically on the line. -2 was 0.4. -1 is 1. 0 is 2.7. 1 is 7.4. 2 is 20. It's somewhere way up here. We don't even have it on our graph. So we'll just do something like that. And that's what that graph would look like. Okay, question. Okay, so we can use this to calculate interest, right? So we can do simple interest, which is just my interest. It's my principal times my rate times my time. That's simple interest. It doesn't compound or anything like that. That second formula, though, is if I want to compound so many times a year, maybe I say I'm compounding monthly, right? If I'm compounding monthly, that means I get 12 calculations in a year. And so that is my N is the number of compounds per year. Now, sometimes you can have interest that is compounded continuously. If you have something that's compounded continuously, then you have to use a whole different formula. And that's what I call this one PERT, because it's P times E raised to the RT. Okay. And that is when your interest is compounded continuously. Compounding continuously is very similar to compounding daily, right? So if you did this formula here and you did it daily, then my N is equal to 365. And it is very, very close. It'll be maybe a penny or two off from your continuous compounding. Okay. So if you saw something that said yearly, if it's compounded yearly, then n equals 1 because I compound one time a year. Another common one is monthly. Then my n is going to be 12 because I have 12 months in a year. Quarterly is going to be n equal to 4 because I have 4 quarters in a year. And then, as I said, daily is my n equals 365. So those are the more common compoundings that you will see. Okay. So the problem that we have here, we're going to look at 3 different ways. We're going to look at compounding annually, compounding quarterly, and then compounding continuous. Okay. So first, we know that our principal is $15,000. That's how much we're investing. Our interest rate is 2.5%. We need to put that into a decimal form. So R equals 0.025. And our time for all 3 of these is 7 years. Okay. When we're compounding annually, we add in that my n is equal to 1. Okay. And so if my n is equal to 1, then that gives me A equals, we're going to use this P times 1 plus R over N times N to the T. So that is 15,000 times 1 plus my rate of 0.025 divided by 1 raised to the 1 times 7. Okay. And that simplifies to $17,830.29. Don't round the cents away on your homework. Make sure you keep it out to 2 decimals. Let's copy this down here for our quarterly one. Change the color. I'm going to actually just change the font of the things that we're going to change. Okay. So in this case, now my n is equal to quarterly. So my n is equal to 4. So that changes in those locations of our equation. Okay. And we will simplify that down to $17,858.96. So now you can see that if I'm compounded one time a year, at the end of 7 years, my 15,000 will be grown into 17,830. Now, if I compound quarterly instead of just one time a year, I get interest paid to me 4 times a year. Then my interest now is making interest. And so now I'm going to have $17,859 roughly at the end of those 7 years. Okay. Question. So for compounding continuously, though, we have to use our PERT formula. And so our principal is 15,000 times E raised to my R. My rate is 0.025 times my time. That is 7 years. Okay. And that will simplify to $17,868.69 over the span of that 7 years. Okay. Question. All right. So you'll see some application problems with exponential functions. You guys will not have a word problem with the exponential functions. You may have it with what we did on the previous page, but you won't have one where you're calculating the half-life of something like we are here, okay? So half-life, if you think about it, if you have chemicals or you have just things in general, like we look at stuff in the landfill, right? Like we're trying to do recycling and things like that. And different products have longer decay rates than others, right? And so really that's kind of when you think about a decay rate, that is thinking about its half-life. So in this case, we're looking at a weapons grade plutonium is comprised of 93% plutonium 239. And the half-life is 24,000 years. Okay. So that's telling us that in half of its life, how much is its strength, right? And so if we look at an example of the 24,000, if we want to look at it for the 24,000 years, right? How much is left after 24,000 years? If I start out with half of a kilogram, let me get a different color. If I start out with half of a kilogram, how much of that is left after 24,000 years? Okay. And so that would just be my 0.5, my half-life, 24,000 years divided by the 24,000 years, because that is its half-life. That is going to give me 0.5 times 1/2 times 1, which is 1/4. So that makes sense, right? 0.5 goes to 0.25. So it takes 24,000 years for it to decay just to half of its strength. Okay. So how much would be left after 72,000 years? So that would be 0.5 times our 1/2. Now we're looking at 72,000 years with the half-life of 24,000. So this is 0.5 times 1/2 cubed. And so this is going to be 1/16. Okay, so we're going to have about an eighth of the original amount remaining after 72,000 years. So you can see some things take forever and ever and ever to decay and go away, whereas other things, and a lot of times, you've probably noticed like a lot of restaurants and stuff, if you get carry out, a lot of them don't do like the styrofoam anymore, because styrofoam took a lot longer to decay than, paper or the cardboard or other things. And so in an effort to be a little more environmental friendly, those sort of things have transpired over the years. Okay. Question. Let's look at one more type of example that you guys might see in your homeworks. So this one says a 2010 estimate of the population of Mexico was there were 111 million people with a projected growth rate of 0.994% a year. So not quite 1% growth a year. So at this rate, the population can be approximated by the formula you were given here. And we also know that T is 2010, right? So this is T equals the number of years since 2010, okay? So if I wanted to know 2010, I plug 2010 in here. The number of years since then is 0 because it is its year, and you would get the 1.110 or 111 times 1, which would be 111 because, right, anything raised to the 0 is 1. Okay, so let's look at this problem then if we let t equal 4. So that would mean we're looking at the year 2014. So if t equals 4 or year equals 2014. Okay, so if we look at that, p of 4 equals 111 times 1.00994 raised to the 4th. That's approximately 115. So there's 115 million approximately in 2014. Okay. So what if I wanted to look at P equals 75? So T equaling to 75. Well, 75 or our year equals their 2010 plus 75. So that is our year is 2085. So what would the population in Mexico be approximately in 2085? So this is P of 75 equals 111 times 1.00994 raised to the 75, and that is approximately 233 million. So there's approximately 233 million people for the population of Mexico projected in the year 2085. Okay? Question. All right, so let's go ahead. So that is all of section 2. Before we move on to section 3, let's go ahead and take our 10-minute break. So it is 7:40. So let's come back at 7:50 and we will tackle the last section of the evening. Okay, it is 7:50, so let's go ahead and continue on with tonight's lecture. So we're moving into section 3.3. This is where we'll talk about logarithmic functions. So last section we looked at exponential functions. This section we'll look at logarithmic functions. And so now basically you've probably seen before y equals log, and then that b down there and the subscript is the base. If there's no value there, it's just assumed that it is a 10 and it's our regular standard base 10. And that is equivalent to saying that we have some b raised to the y x. So this is kind of, you're thinking inversely, right? Because before our y was down irregular and our x was up in the exponent. Now we've switched those roles and our y is up in the exponent and our x is down on the baseline. Okay, so the first set of problems that we're going to look at here is we're just trying to rewrite this equation into exponent form. Okay, so we'll look at what we were given here as a guide. So we have y equals log base b of x. Okay, so if we use that, so that's telling me that this is y, that my y equals 2, my b equals 4, and my x equals 16, right? So if we do that, then if I want to change this into exponent form, that's my b raised to the y is equal to x. Okay, and that's true, right? 4 squared is equal to 16. Okay, so for our next one, we have here that y equals -1, b equals 5, and x equals 0.2. So this is 5 to the -1 is 0.2. Okay, question. So y equals 0, b equals 8, x equals 1. So this one would be 8 to the 0 is equal to 1. Last example of this kind, we have y equals 0, b equals 23, x equals 1. So this is 23 raised to the 0 is equal to 1. Question. So this next set, we're taking our log and we're taking our equation form and we want to write it in logarithm form. Okay. So in this case, we have that our b equals 2, our y equals 4, and our x is equal to 16. So we're going to put that into log form. So that's log base b. So my b is 2. X is 16. And so that is equal to y, which is 4. Okay, question. Okay, b equals 27. Y equals 1/4. X equals 3. So this is going to be log base 27 of 3 is equal to 1/3. I wrote 1/4 here. It's 1/3. Sorry. Okay, so we have b equals 1/4, y equals -2, x equals 16. So this gives me log base 1/4 of 16 is equal to -2. Any questions going from equation to exponent or logarithmic form to equation or exponent form? Okay. So as I had mentioned on the previous page, if you don't see a base with them, so if this doesn't have a base down here, where you see here it's a 10, then so when you see log without a base, then you can just assume that that base is 10. Okay. And so your calculator can do log base 10s, but it can't do log base 2, log base 3, etc. That's why you have to know those conversion factors. Your calculator also does a natural log. That's the log base e. And so that's the key on your calculator that says LN. Okay. So for this first problem here, if we have log base 12 equals 44, that is equals y, right? So that we could just say that's 12x equals, not y, x, equals 144. So x times x raised to what exponent gives us 144? Well, that would be x squared. So in this case, x has to equal 2. Okay. We have, this one would be 64 raised to the x equals 8. So 64 times raised to what power is going to reduce it. So you know it's going to have to be a fraction because it's 64 is larger than 8. So in this case, it would be x is equal to 1/2. So if you put x 64 raised to the parentheses 1/2, you will get 8. And we kind of also know that because 8 squared is equal to 64. So if we want to get half of that, the squared is over here. So then 64 to the 1/2 then is going to give you 8. So that could give you a little bit of a clue as well. Okay. So this one is going to give us 3x equals 1/27. So in this case, x is equal to -3. So x 3 times 3 times 3 is 27. But in order for it to be that fraction, 1/27, then we have to have our x as -3. Okay, questions on that? Okay, as I mentioned, we have some examples here with our natural log. So, and with natural log and then our common logs and natural logs here. So this one is the same as saying 10 squared. Well, 10 raised to what gives me 100, right? And so that would be 10 squared equals 100. Okay, so for this next one, that's 10 raised to what is going to give me 0.0001. And in this case, it's 10 We went 1, 2, 3, 4 places, so that's -4 is equal to 0.0001. Okay. So the thing with the ln, when you are looking at ln and e together, you could think of those as kind of countering each other out. And so in this case, we would end up with e to the -3 is equal to e to the -3. And similar over here, e to the 10 is the same as e to the 10 because that ln is our natural log and it equals itself. Okay. So just as we did with the e in our calculator, we could do the same. Let's practice a little bit with the log and the natural log in our calculator. So if you put log 43, you should get 1.6335. If you then take 10 and raise it to the 1.6335, you'll get back to that 43 value. Okay. So put log 200 in your calculator, you should get 2.3010. So then when you put 10 raised to the 2.3010 in your calculator, you get 199.986, which is a pretty close approximation of 200. Okay. So let's look at number 16 here. When we put this in our calculator, we get a -1.1308. So 10 to the -1.1308 is approximately 0.0740, which is back to the original that we plugged into the calculator. Okay. Plug ln of 200 into your calculator, you should get 5.2983. Then you can take e and raise it to the 5.2983, and you'll see that's approximately 199.9965, very close to that original 200. Okay, the last example on this one is you plug in ln of 1.005, you get 0.0050. So e to the 0.005 is approximately 1.005, and that checks out as well. Okay, question. Okay, so we have some properties of logarithms, just some of the basic ones, that if you have log base b of 1 equal to 0, and that is because b to the 0 is equal to 1, right? So these are all those things that we were translating with earlier. And so if you have log base b of b to the x is equal to x, and that is because b to the x equals b to the x. Okay. So let's look at some examples here. So in this case, we are looking at, so we have log base b of b. So this one is what we're looking for here. So we end up with log of 19, 19, that's going to equal 1, right? And that's going to equal 1 because 19 to the 1 is 19. Okay. And we're going to look at log base 10 of 10, right? That again is also going to equal 1 because that is saying that 10 to the 1 is equal to 10. When we look at the ln of e, that is also equal to 1 because e raised to the 1 is e. Okay. Log base, so this is 273 raised to what is going to give me 1. So anything raised to the 0 is going to give me 1. So this one would be equals 0. Okay. This one would be 1/8 raised to what equals 1. Again, that is 0. This one is 30 raised to what gives me 30 to the 10. So that would have to be 10. Any questions so far? Could you go back to... Is this the one you are asking to go back to, Brandon? Okay. Are you good? Did you have a question? Okay, you're good. Okay, so now we have e to the negative 12 is equal to e to the negative 12, right? So those end up being a little bit easier when they have the e involved. Log or 10 raised to the log 14. So these again too, because it's together, it really is then that's just going to equal 14 because the 10 log base 10, those kind of counter each other out and it leaves us with the 14. Similar over here where we have log base 8, 8 raised to the log base 8 of 5 is just going to be the 5. Okay, because you could think of these as kind of countering each other out. Okay, question. Okay, so just like we had with our exponential functions, our logarithmic functions can have transformations as well. So if we have the h there with the x, that's going to still tell us whether we're having a horizontal shift to the left or the right. That k out there at the end will tell us if we are shifting our graph up or down. And the value in front of the log, that helps us with the reflection of the x-axis. Okay. So if we had our function here, y equals log base 3 of x, if we wanted to write that in exponent form, that's the same as 3y equals x. Okay. So in this case, our y is the -3, -2, -1, 0, 1, 2, and 3. And what we're having to calculate now is our x value. Okay. So this would be 3 to the 0. I mean, not 3 to the 0, 3 to the -3, which is 1/27. This is 3 to the -2, which is 1/9. 3 to the -1, which is 1/3. 3 to the 0, which is 1. 3 to the 1, which is 3. 3 squared, which is 9. and 3 cubed, which is 27. So let's see that over here. You could see that when we have -3, we're really, really close to 1/27. So you can't even hardly distinguish from the actual line itself. So that's kind of what that graph would look like over here. We didn't have to draw it out here. I just put what it would look like so you can get a visualization of that. Okay, question. Okay, similar. We have something that's a little bit more complex, right? So if we're looking at this parent, the parent in this one is going to be y equals log base 2 of x. We're going to shift that left 1 unit, and we're going to shift that up 2 units. Okay, so -3, -2, -1, oops, wrong column, sorry. -3, -2, -1, 0, 1, 2, and 3. So the thing about logs is they have to be positive, right? If try to put in a negative log or a negative ln, and you'll see that there's an error, right? So when we put -1 in here, you'll see that that comes back. You get an error because you can't take the log of 0. So what I'm going to do is let's look at -1/2 instead, because these other ones we can't use because it will give us something that's undefined. So when I plug in a -1/2 in there, solve it out, I get that my x is equal to, sorry, sorry. So we do want, our x isn't in the exponent now, sorry. We don't have to, we can put it on our y. So we can have, our x. So still we'd want the -1/2 on the x, 0, 1, 2, and 3. We can't have an x value less than -1 because it'll give us a 0 and you can't do the log of 0. Okay. Or the log of a negative. So when I plug in 1/2 in here, do this out, I get my y is equal to 1. When I plug 0 in, I get 2. When I plug 1 in, I get 3. When I plug 2, you have to approximate, and it's 3.6, and 3 is going to give you 4. And so then that's what the graph would look like over here. So remember, we have our original graph, and so this is shifting it left 1 unit and up 2 units, right? So we were left 1, up 2. And then we get this blue graph here. So again, transformations work very similar. You may find in the beginning that it's easier to build the table. That's kind of how we did it for the lecture here, to help you see how we get each of those values. Over time, you may be able to just shift and do the transformations and not need to build out the table. But in the beginning, you're probably going to need the table to help you with those transformations. Okay, questions? So I do have here the top half of the page is really, it's just the informative thing. So showing you the difference between our exponential graph and our logarithmic graph. So our exponential graph is graphed in blue there, and the logarithmic is the red. And so you can see that those are inverses, right? Because our x values and our y values are transposed, okay? And so there's the domain of each of them and the range of each of them. So you can see that the domain and the range values actually flip-flop, whether you're talking about the exponential or the logarithmic. You'll have horizontal asymptotes for our exponential. You'll have vertical asymptotes for the logarithmic. And our exponential graphs, they will pass through the point 0, 1, whereas our logarithmic graphs are going to pass through the point 1, 0. Okay? So I put that there so you guys can use that as a reference. But now let's take a couple of examples, and we want to give what is the domain and the range of these two functions, okay? And what are the vertical asymptotes? So for this first one, our domain, you can see this is going to go on and on forever. There's no restriction on our y values, right? Because those are going to grow. But you could see that this is 1, 2, 3. This is growing really, really close here to this green line that I just drew in here, but it's not actually crossing it. So our domain here is going to be -3, infinity. Now I have a parentheses on -3 because I get really, really close to it, but I don't actually ever cross or touch that line, okay? My range is what are my y values, and you can see this one, we're unrestricted, so we can go from -infinity to +infinity. And then, as I already mentioned, we have that vertical asymptote at x equal to -3. Okay? Question. Okay, for this next one, you could see we're going again all the way up into infinity, all the way down into -infinity, but this time we are really approaching this line right here. So in this case, my domain is going to be 0, infinity. My range is going to be -infinity to +infinity. I have that vertical asymptote at x equals 0. Okay? Question. All right, so the last thing that we have here, this is the same as saying the log of, and we can factor this. This is x minus 4, x plus 1, okay? So I can see I have a vertical asymptote at x equal 4 and x equal to -1. So if we look at that as our boundary points, right? So we have -1, 0 is here, and 4 is here, right? So we know that we can be on these sides here, right? Side cannot equal 4 or -1. When I look at this, that's going to give me, I'll be positive in this range, negative in this range, and then positive in this range again out here. Okay, so we can see that our x cannot take on these values here, right? So our domain in interval notation is going to be from -infinity to -1, and then again from +4 to positive infinity. And then our range can be any values because those are going to go from, our y can go from negative infinity to positive infinity without any restrictions. Okay? Questions? What was that for? Any questions on this one before I go back to the previous page? I had a question in the chat on that. The 3.6, what was that before 3.6? Does that answer your question in the chat?
Yes, Professor.
Okay. All right. So that is all of the new material for this evening. It gives you guys 3 sets of problems to work on over the week in your ALEX. Do you guys have any questions, comments, concerns, anything that you would like to go over more of? If you guys don't have questions, that is all the material we have for this evening. So you're free to go. I will stick around to answer any questions that you all have or anything of that nature. All right. But if you don't have questions, you're free to go, and I will see you all next Monday.